Hello, everyone. My name is Ryan Boyd. I'm a developer advocate at Google focused on our big data services, and we're here today to talk about crunching big data with Google BigQuery. If you have any questions, we will try to save some time for the end. We'll have about 5 minutes, but you can also reach out to me on Google+ or on Twitter, and I'm happy to answer any questions you have. All right, so the first thing that we need to define here, though, is how big is big. Now, you guys all have your definition of big data. In industry and in the press, the definition can often be very different. There's an upcoming big data hackathon, and one of the data sets that they were planning on using, or are planning on using, we're sponsoring this hackathon, so I don't want to put them down too much, but is a list of beers and the attributes of those beers. I can't see how that could possibly be considered big. But you guys, you probably have a much bigger definition of big data than even what we'll be talking about here today. And if you have problems that you want to solve with our technology that are bigger than what I'm talking about, let me know. We're happy to stretch the boundaries of this. So we asked like 1 million rows, 10 million rows, 100 million rows. What I'm going to say is somewhere around 500 million rows is the size of the data that we're looking at with BigQuery. Hundreds of millions to billions of rows of data. Our limit on the size of a row is currently 64K kilobytes. And so that kind of gives you the general idea of what we're looking at. Hundreds of gigabytes up to terabyte-sized tables. But we often shard this data as well. Big data at Google. Google certainly knows big data. I'm not going to claim to be an expert in all of this, but every minute, 60 hours of video are uploaded to YouTube. There are 100 million gigabytes in the Google search index, and that is a number that's been used since 2010. Imagine what it's at today. And there are 425 million users of Gmail. All these different products require and also produce massive amounts of data. At Google, all of our decisions are based off of data. When our product manager decides they want to launch something or add a feature or what have you, they really need to have data that backs up what they're doing. And we need tools to analyze this data. And we want answers in seconds, not in minutes, not in hours, not in days. We want answers in seconds so that we can do this iterative analysis on how our products are being used and on the underlying data that our products are producing. So it used to be for many companies, if they want to do this analysis, many of the customers working with, it started off with a single relational database server. Pretty simple. You can scale vertically, add more memory, CPU, faster hard disk, whatever. But Google looks at it from a perspective of hundreds of thousands of servers that we have around the world and says, how can we process our data on that? With this type of infrastructure, we're not worried about building indexes. We're actually OK with things like full table scans. And that has a lot of developers quite confused, but probably not the folks in this room. But we built this internal technology called Dremel on that understanding, on the understanding that we can actually do full table scans across terabytes of data. And we do it for things like, or we use it for things like this, and they're really diverse. So finding the top installed applications on the market. So think of the Google Play Store or the or the Google Apps Marketplace or the Chrome Web Store. We can do simple queries, SQL-like queries. PMs can even do this. Most of our PMs have CS degrees, so I shouldn't bust on them too badly. But simple SQL-like queries like this and get a result in about 20 seconds, looking over every single install that happened. And there's no indexes or anything taking place here. So this looks over the install log for 2012. We could just as easily look over multiple years or a specific month. And I'll talk to you about data sharding here a little bit later. We also, all of these markets are hosted on servers, and we need to understand how our servers are performing. So if we want to do something like finding the slow servers in our environment, our operations folks use the Dremel technology as well. So they can run a query like this, basically look over the logs, find all the responses that are taking greater than 4 seconds, group those by servers, and order it by the count, descending, and again, get a result in 20 seconds, and looking over, in this case, somewhat live data. We don't have real-time streaming yet, but a couple minute delays or what have you on your data, and you can find all those servers that are performing slowly and then dig deeper. And that's really what this technology is about, being able to dig deeper because you have all your data in one place. You're not worried about building indexes. You can run those full table scans and do this aggregate type analysis. So BigQuery is our technology that gives you this power. BigQuery is an API. It is a REST-based API. It doesn't require much computer science knowledge. It requires ability to make simple HTTP requests. And you can even do most of it with our UI. But at heart, it's an API. It's an API that allows you to store your data with the reliability, redundancy, and consistency that Google expects of its own data. It's using our same underlying infrastructure. So you can go from data to meaning at scale quickly. So we have developers using it for as diverse a range of use cases as Google uses the underlying technology internally. We have folks using it for game and social media analytics, infrastructure monitoring, advertising campaign optimization, and sensor data analytics. A lot of the benefits of the cloud, this last one kind of points that out. We have a lot of people that are collecting data all over the world, and they need some central place to collect that and then run aggregate analysis on it. So I'm going to start by talking about the architecture of BigQuery. This is usually a section that I save towards the end, but I figured if I don't talk about it up front, you guys will have lots of lingering questions. And then I'm going to dive into how we allow you to prepare your data, visualize it, and then some example types of queries. And of course, you're going to have some live demos here too. So the underlying architecture. This is a great quote from a 16th century Italian philosopher monk that says, if you do a full table scan over a 1 terabyte table, you're going to have a bad time. Of course, that's if you're trying to do it on a single machine. If you're doing it in parallel and you have 10,000 disks and you have 5,000 processors, you can do that sort of data crunching. And that's what we rely upon with BigQuery. It's a column-based data store. So we store the data in columns for a couple reasons. One is it's highly compressible. The second reason is that it reduces the amount of data that we actually have to read when running queries, because most often the queries are only touching specific columns in the underlying tables. And because it reduces the amount of data that we have to hit to run our queries, it also reduces the overall cost. So BigQuery is a paid service. We charge $35 a terabyte of data that's accessed when you run your queries. And there's some storage costs as well, but those tend to be pretty negligible. Though overall, you really want to reduce how much data you're hitting, but still obviously get the answers to your needs, or answers to your questions. And the BigQuery architecture is a typical tree-like architecture like this. The query comes in at the top, gets distributed down to the shards. Every shard gets its own set of data from the Google file system, and on the orders of tens of megabytes of data. And each shard is able to process its set of data itself without communicating with any of these other shards. So it processes its set of data, and then as you go up the tree, imagine if like 2 of the leaf nodes were doing counts, then the mixer will do the sum of those counts. So anything that mathematically you can combine as you go up the tree, BigQuery is really good at. And all of the communication here is happening directly between the nodes on our back-end fabric. We are not actually writing any data to disk during this process. That's another reason we gain efficiency over some competitive, or some may say competitive technologies like MapReduce. We're not writing to disk at all. All we're doing is reading blocks from disk on the leaf nodes in a distributed fashion. All right, so BigQuery. I already talked about this, but it is an API. I want to emphasize that point over and over again. We've gotten criticized in some of the tech press for our UI not being sexy enough or not having enough functionality. We're designing this as an API for developers to build things. And developers build things in-house within their own organizations. They also build products on top of it for other organizations. All you have to do is upload your data to Google Cloud Storage. And then your data is loaded from cloud storage or ingested, as we call it, into BigQuery. And the ingestion process is pretty simple. It looks like this. This is just a JSON object representing your data. And then you form that JSON object and post it to our jobs endpoint, and we then ingest the data into BigQuery. And the question everyone has is, how long does this take? I did Wikipedia revision history data, about 450 million rows of data, somewhere between 15 minutes, a half hour for it to ingest it till you can start running queries on it. And because there's no indexing, it's immediately available. So then you can query away, and the endpoint for querying is the exact same endpoint. You post a job, and you start querying away. And we'll show you what that querying looks like here shortly. But first, Java, Python, .NET, PHP, JavaScript. Even if you don't want to write the REST queries by hand or deal with OAuth 2 and that sort of thing by hand, you can use one of our libraries. There are others in this more category like Ruby or Go for those of you who are going to ask that question. Here's an example using the JavaScript library. And this, again, is forming up this really simple job at the top here as JSON, and then it's executing and calling this callback function, which is logging the response and looping through each of the rows of the response and doing something. So this sample, I'm missing a few lines of code here, but say about 15 lines of code of JavaScript, and you can really easily query these massive data sets. So I mentioned our UI that some consider not quite sexy enough. I actually consider it fairly decent, but let's actually jump over there. And we have in my browser here the BigQuery UI. And on the left-hand side here, we have public data samples. I realize this might be better if we get a little bit bigger. But public data samples over here is basically a list of all the public data that we have exposed in BigQuery. You can query this public data up through 100 gigabytes of it in any given day for free, with a little asterisk next to it for the legal folks. And I'm showing you actually one of the data sets, which is the natality data, which is US birth statistics, basically a row for every baby born in the US since 1969. It's only 137 million rows, but the same types of querying will grow as our population grows in a relatively constant fashion here. So in this case, I'm doing a query here saying select average weight in pounds, and remember there's no indexing or anything like that, but I can get the average weight of all babies born in the United States in the last 30 or 40 years with a simple query like that, 3.2 seconds, and because I'm only going over one column of data, it's only 1 gigabyte here. But let's take that and show you kind of this iterative nature that we like to do. And I was kind of curious as to the average weight in pound of babies born in 2003 in Ohio, where their mother did not smoke cigarettes or said they did not smoke cigarettes. If you run a query like this, again, only 2.3 seconds, we get the average weight of a baby as 7.3 pounds. And if the only thing we do here is change that from false to true and run it again, 6.8 pounds. There's a half a pound difference between the weight of a baby born to a mother who says that she smokes cigarettes versus not, which I'm not from the CDC. I'm not going to attach a meaning to that, but it's kind of interesting. And that's the type of thing you can really just drill down in data, even if the data is super huge. Let me see if there is one other thing. Because you're doing full table scans, we also have this Wikipedia revision history data in here. And I want to see like all of the number of revisions to Wikipedia pages that started with a capital G or included a capital G and ended with a lowercase e as a regular expression match. Imagine performing regular expressions across hundreds of millions of rows in traditional technologies. It's not a simple API call, but in this case, it is. 6.1 seconds, and we found out that Greece is the most revised page in Wikipedia that has a capital G and ends with a lowercase e. Useful data, I know. I'm sure you can do more useful things with it. Unfortunately, we're really bounded by the amount of public data that's available out there for demos, but we're coming up with some nice ones. I'm working on a data set that's about 6 terabytes of Wikipedia page view counts, which should give us some interesting insights. But preparing your data, The first thing I want to mention here is it's not your relational database. You're taught in school to always normalize your database so that multiple kids born to the same parent have one parent record. Simple, and it allows you to maintain consistency when you're updating things a lot. Well, in the case of BigQuery, it's an append-only data store, so you don't have to worry about that consistency. And we ask that you normalize or denormalize your tables to look something like this. Basically allows us to be a lot more efficient in your queries. We can support joins in a small sense, and I will show you what those look like shortly, but also talk to you about kind of the underlying architecture of how we do the small joins. And you'll see it's a little bit more expensive than on other systems. You also generally want to shard your data when working on a system like this because we do full table scans of everything and you pay for every query that you run. You want to shard your data into kind of shards that you would typically look at. So if there were 1 billion babies born in the US every year, you might want to shard on a per year basis all your babies, and then you would have these half dozen different tables. And then you can do a query on a particular year. But if you want to do queries across multiple years, you can easily do that as well by just unioning your tables together. But it reduces cost for you. The time is often quite the same, but it reduces the overall cost for you. It's a CSV formatted file that you ingest your data in. Very easy to produce. It's not as flexible as we like. It doesn't currently support sort of the nested repeated values and things like that that Dremel supports. This might be a good place to mention the Dremel white paper. There is a public white paper on Dremel that has a lot more technical details if you want those that I'm giving you here today. But you can read all the details of the experiments that they performed and things like that. And one of the big features of Dremel is nested repeated fields. We support that in BigQuery, but our ingestion format is currently this CSV-based format, so it's hard to get it in CSV. Working on that. Of course, you can use a variety of tools to prepare your data, and our customers do. App Engine MapReduce, or commercial ETL tools, Pervasive, Informatica, Talend, have all added support for BigQuery. And then there's the Unix command line favorite, awk, sed, things like that. That's a lot easier if you're trying to do a really quick load into BigQuery. Visualizing, it's hard to really understand big data without visualizing it, and there are commercial tools, but then you can also visualize yourself using something like Google Spreadsheets. So this Google Spreadsheets is using AppScript, which is a JavaScript-based server-side executing language that you can put within your spreadsheets. And this is about 70 lines of AppScript code to run a query against, in this case, the 137 million rows of data, and then produce pivot tables and charts and that sort of thing. This graph is actually my personal little side project of looking at that natality data and comparing the age when a mother gave birth to her first child in blue states versus red states. So in blue states, the mother gave birth to her first child about 2 years later than in red states currently, and that gap has actually been widening over time. But fun little exploration. Again, I'm not a statistician, don't want to attach meaning, but you can also, of course, do custom code to do any of your visualization. So Google has a visualization API that allows you to do a wide variety of different types of charts. Here's one of them, which is a map. And this map was produced in about 70 lines of JavaScript as well. And you can see here, this is the average baby weight in 2000, with the darker babies being, or the darker color being the heavier babies. And you can see that, I guess, in the colder states, the babies are a little bit more insulated, which is probably beneficial for them. So when you want to run your queries, there are the standard aggregation queries that you're probably familiar with. Nothing extremely complex here, but if there's additional functions that you're looking for that, like I said, can be easily combined as you go up the tree, let us know. And then regular expressions and things like that can be really powerful. The things that you would never think of running over every single row in hundreds of millions of rows or billions of rows of data, you can do when you're doing full table scans and expecting it. Small joins. This small joins was actually something I mentioned earlier. You want to denormalize your data when loading into BigQuery because you don't really need the normalization to occur. Some people still in their brain think in a normalized fashion, which is fine. And we do support small joins for things like lookup tables. So the red state, blue state stuff that I showed you, I had a lookup table that was just every state and whether it's red or blue. It still can make things slower, and I'll show you why. This is the diagram that we saw earlier of just generally how BigQuery processes a query. And this is what we do with the small joins. Every one of those yellow boxes represents the smaller table that we joined against the bigger table. So we run still this one-pass analysis where all of the leaf node shards are getting their chunk of the large table. But then they're also processing and joining that with the small table because each of those shards gets a copy of the small table sent to it over the network for processing. So you can imagine that if you made that too large, then obviously the network traffic to pass this along would be challenging. So I mean, I think in general this illustrates the point of what BigQuery does and what Dremel's underlying infrastructure does. And that's really try to optimize performance. There are certainly some things that we could do to make it possible to run these queries, but we really want to get those results back in seconds. So we want to constrain you a little bit to getting those results back in seconds and to make you think differently about how you design your data when you ingest it, et cetera. We also recently did launch Batch, though. Kind of going against what I just said, but this is from a cost perspective. So we added this new functionality called priority, and you can specify a priority of batch on your queries, and basically the queries will return anywhere between 30 minutes and 3 hours. And this is really to avoid people from needing to use multiple different technologies together. So we would have a lot of our customers who would use MapReduce-based technologies to run their batch queries and batch reports. And then they would hop over to BigQuery and use it for their ad hoc analytics. And when you have to host your data in 2 different places to run 2 different types of analytics on it, that's a problem. When you have to compose the way that you're running your queries in 2 different ways for 2 different systems, that's a problem. But they did this primarily for a reason of cost, because our pricing on BigQuery is based off of doing these ad hoc live analytics. And sometimes you just don't need that. So the batch, basically 30 minutes to 3 hours, and it's about 40% of the cost as we schedule these jobs kind of in between the interactive jobs. So that's it. BigQuery is an API, column-based data store. You can do full table scans quickly. Aggregates are what it's really good at, and there's commercial tool support. And we've talked about the wide range of use cases from analyzing sensor data to marketing analytics to understanding server infrastructure, downtime, and that sort of thing. So now I ask you in SQL for any questions that you might have.
So I would be thrilled if you would just answer the following query, which is Google has about at least 10 database systems. And so you've got MapReduce, you've got Bigtable, you've got BigQuery, you've got ... And Shiv has written another SQL database system that's for your ad serving. So you've got a whole bunch of them. Could you just tell me what percentage of your internal Google use uses each of these systems? Sort of, so I hear anecdotes that MapReduce is out of favor. So could you just tell us what the current usage of all your various things is in Google?
I think it depends on the engineering team, and I can't give you a precise answer. I will say, it depends on the use case, and we do have, MapReduce-based technologies. There's a lot of things that are moving to like a Flume-based system, which we published white papers on as well. MapReduce is great for some types of things. If you want your answers in minutes or hours, and you want to do a lot of processing and interrelated queries between rows and things like that, where you're okay with multiple passes over the same data and writing to disk and reading from disk again. The Dremel-based technology is great for things like our log files and for kind of transactional data that we're just trying to query these aggregate queries over, and that's the preferred mechanism for that type of query. Yeah, there's other things like tensing, et cetera. Sorry? I'm ducking the answer partly because I don't have the full answer, and partly because even if I did have the full answer, that's not something we've published before, so I probably couldn't tell you. But I would say it's in transition, right? As we build new technologies, it's in transition to some of the newer technologies. The MapReduce stuff moving to Flume, but as for the exact percentages, I don't have that for you. Sorry.
Yeah, Carlos Malzahn, UC Santa Cruz. I was wondering, when you say ingest, how much data do you actually move? Can you tell us how data or movement intensive that process is, or is it something that you do in place?
So generally, to ingest your data into BigQuery, you load it into Google Cloud Storage, which is an S3 compatible storage bucket. And then Cloud Storage moves it over to BigQuery. BigQuery does talk directly to Cloud Storage, but it is moving all of that data in our data center into BigQuery. In terms of in place, the underlying infrastructure does allow us to look in place. The Dremel infrastructure does allow us to look in place at Bigtable tables. It does allow us to look in place at at basically stuff stored in our Google file system, but we don't really use that right now for BigQuery. We're definitely, require the developers, because they have their data usually sourced outside, required to move it to cloud storage and then to BigQuery. There is a step that you can skip there, the cloud storage step you can skip and go directly to BigQuery. But a lot of the tools and libraries don't support things like the resumable upload and all. So people are trying to make hundreds of gigabytes requests over plain HTTP, and there's errors that happen along the way, and those things fail. So that's why we generally say go to cloud storage first and then over to BigQuery.
Hi, Feng from VMware. Just wondering, you only have table scans without index. Does it have anything to do with your pricing model? Basically, you charge by the data you scan.
Yeah, I mean, we basically charge for the columns that you accessed and the size of those columns times the number of rows in your table. There is a full table scan for every single query. There are, of course, things that we could do to optimize that. We don't want to have to maintain indexes, so we don't do index optimization. I think the best optimization we could probably provide for some of our customers would be a caching layer. Most of our customers end up building that caching layer themselves, so if they're running the same queries over the same tables often, they cache that themselves. But we could make it a little bit easier on that end.
Hi, Mehul Shah of New Data. So I have two questions. Question number one: if I have terabytes of data, how do I get it to you? If it wasn't born on the Google Cloud. And the second question is, Dremel, at least the paper that was published a year ago, talked about nested relational model, and you guys didn't launch with that, and you said it's coming. So why not, and when is it coming?
Okay, so I said we're working on that. I didn't say it's coming. There's a minor distinction there. And so I don't have a particular date for you, but I would be optimistic. I'll say that. That answers the second part of your question. The first part was the size of your data and how you get it to us. Right now, you get it to us via your bandwidth, and hopefully your bandwidth is good. Multiple terabytes of data is fine. It takes a little bit of time, depending on where you're coming from, but I definitely understand. So if you have more data that you want to load to us or want to load into BigQuery and you're bandwidth constrained, definitely let me know, and we can see if there's other options.
Hi, Ari Rekapalli, University of California, San Francisco. What's the performance like on EAV data? EAV is entity attribute value.
So you're saying nested data then? Is that right?
EAV is basically like RDF.
I would believe you're referring to nested data in my terminology, but I can chat with you later. Basically, in nested data, the performance is actually really good, just as good as you saw with data that's not nested. But I would read more of the Dremel white paper if you wanted more details on that, but happy to chat afterwards as well. We have 37 seconds. Anyone?
So you mentioned about interactive queries and batch queries. What are the challenges that you had to put both these two different types of queries on the same system, or does the batch queries go to MapReduce systems?
So the batch queries do not go to MapReduce. They are running on the same system, and I think it actually makes things easier for us because we have time slots when not all the machines are fully utilized, and they're not all fully utilized because we want to have space to grow for the interactive queries and want the interactive queries to return quickly. And that allows us to schedule some of these batch jobs on those machines when they would otherwise be idle. And give up those batch jobs and rerun them again or what have you if interactive queries come in. So the scheduling is actually beneficial for us. I wouldn't call it a challenge, I'd call it an opportunity. All right, thank you very much.